Okay, so let's say you're in a job and your base salary is $15,000 a year, and you also earn an 8% commission. The expression 0.08x plus 15,000 would represent your salary, where x represents the sales. So the way this would work is you would multiply 0.08 times the amount of sales, and that would be your 8% commission. And then on top of the commission, you have your $15,000 base salary. This is called an algebraic expression. So instead of just an expression where we're adding, subtracting, multiplying, dividing numbers, an algebraic expression is going to have a variable like x in it, where x represents some other number. The term that has the variable in it is called the variable term. The term that does not have a variable in it is called the constant term. Constant because it never changes. When I refer to terms, terms are specifically pieces of the expression that are separated by addition. Now, addition also means subtraction. Let me put another expression here that we can look at. X squared minus 2xy plus 4. This has three terms. Now, I said that terms are things that are separated by addition, but then I said addition also means subtraction. And you can see I'm counting subtraction because I'm saying there's 1, 2, 3 terms. But remember, subtraction is just adding a negative. So this can also be written x squared plus negative 2xy plus 4. Then you can clearly see 1, 2, 3 terms all separated by addition. Some other words that we need to know about the different parts of an expression. Coefficient. The coefficient is the number that comes before the variable in each term. So let me write out these terms another way. X squared negative 2xy, and positive 4. If we were to find the coefficient of each of these terms, we would want the number in front of the variable term, the number that comes before. You want to keep the sign as well. Now, each of these is its own separate situation to look out for. With just x squared, there's no number listed in front of x squared, but we know there is a 1 in front of x squared. Why? Because 1x squared means 1 times x squared, and anything times 1 is itself. So x squared is exactly the same as 1x squared. When we see x squared, we know there is a 1 in front, so the coefficient of x squared would be 1. And let me just make sure that 1 is in frame. Negative 2xy, it's not just going to be 2 for the coefficient of this term. It's going to be negative 2. Always keep the sign in front. So 1 was a positive 1. 2 is a negative 2. 4, we don't have a variable to look in front of. But just like when we don't have a coefficient in front of the variable, we know that the imaginary coefficient is 1. Here, when we don't have a variable term, when we have a constant term that doesn't change because there's no variable, we can imagine that there's an x to the 0 power. So again, why can we imagine that? And when we do imagine that, since this is the variable part, we can clearly see that 4 is the number in front. Anything to the 0 power is 1. So x to the 0 times 4 is the same as 1. Don't want that to be 0.1. 1 times 4, which is 4. So again, when we don't see a variable term, when we're in our constant term, we can imagine that's the same as x to the 0 power. Okay. So just to remind everyone where this came from, x squared minus 2xy plus 4 was our expression, and we found the coefficient of each term. The coefficient of this term is 1 because of the 1 in front. The coefficient of this term is negative 2 because of the negative 2 in front. The coefficient of this term is positive 4. Okay, if you still have any questions on this idea of coefficient, don't worry, there's going to be more examples. If at the end you have any questions, feel free to contact me and I will answer them for you. But make sure that you still have those questions by time this is over, because it's quite possible with the repetition, maybe the different ways I explain things, that it'll click before this lecture is over. Okay. Let's review some properties of real numbers. Now it's going to be important that we talked about coefficient and what that means, and that coefficients keep the sign in front of the number. Let's talk about the commutative property first. The commutative property, if we look at the word commutative, you can almost see the entire word commute. Commute means you're moving from one place to another. You're physically changing your location. The commutative property is going to be the one that physically changes the location. If we have A plus B, the commutative property of addition says that we are allowed to physically pick up the two things that are being added together and move them. We can put them in any order. A plus B is the same as B plus A. But when you're moving terms around, you need to make sure you take the entire coefficient. Coefficients can be negative. We saw that. And how do we make sure that when we move things around, we're taking the sign with it, that we're taking the entire coefficient? Well, for that, let's look at the commutative property as it relates to A minus B. Now, there are two different commutative properties. There's the commutative property of addition, and there is the commutative property of multiplication. There are not any more. There's no commutative property of subtraction. But what did I say earlier about subtraction? Subtraction is adding a negative. This we could apply the commutative property to. So A plus negative B, if we wanted to move the terms around, it would have to be negative B plus A. So A minus B is not the same as B minus A. There is no commutative property of subtraction. A minus B can be rewritten, but you have to write it as addition first and then move the terms around the addition sign. Okay. When would we use something like this? That could be a question you're asking right now. Let's say we're working on some problems and pretty consistently we write things like 2x minus 1 3x plus 4. And maybe you get used to all your work with the x in front. Negative 5x plus 7. And then all of a sudden, you come across 2 minus x. Maybe we don't want it this way. Maybe we want it like all the other ones were. You can't just make it x minus 2. that changes it. And I'm going to do a little more focus on that in a second. What you would have to do is realize that that is 2 plus negative x. And therefore, to get it looking like everything else, you would switch around the addition sign, and it would be negative x plus 2. So that, changing a 2 minus x to a negative x plus 2, that's actually a way that we use the commutative property of addition in algebra. Let's take a look at the commutative property of multiplication. It's exactly the same as the addition one. We're going to physically move. We are going to commute the terms. The commutative property of multiplication says that A times B is the same as B times A. With numbers, we can easily see that this is true. If A was 2 and B was 3, 2 times 3 is 6, 3 times 2 is 6. So yeah, multiplying two numbers in any order gives us the same answer. That's what the commutative property is about. It's about saying we can add in any order, we can multiply in any order. There's no commutative property of division. A divided by B does not equal B divided by A. But multiplication and division are related very much the same way that addition and subtraction were. Just like subtraction is adding a negative, division is multiplying a reciprocal. What's a reciprocal? A reciprocal is when we flip a fraction, remember. So 3 over 4, 3 divided by 4, is the same as 3 times, what's the reciprocal of 4? 4 is 4 over 1. So if we flip that, 1 over 4. Now, we can swap those around, but 3/4 would not be the same as 4/3. What you do get, though, is the reciprocal. So that begs the question, wait a minute, if we don't have a commutative property of division, but instead what happens when we divide in the other order, and dividing in the other order is the same as reciprocal. And multiplying by the reciprocal was a similar process to adding the opposite. Does that mean that If we switch subtraction around, we get the opposite, just like when we switch division around, we get the reciprocal. Let's find out. I did say we would take a look more closely at what happens when we subtract in the other order. So how can we test to see if these are opposites? Well, let's see what A minus B is. Let's just pick something. 5 and 3. 5 minus 3 is 2. Okay, so if we switch it to the other order, 3 minus 5, 3 minus 5 is negative 2. So up until now, let's move away from the commutative property. We've used these words, opposite and reciprocal. There are fancier words for these that have to do with their properties. So let's define them for the record. Opposite is represented by a negative sign. The opposite of A is negative A if A is positive. If A is negative, the opposite of a negative is a positive. Reciprocal would be 1 over. 1 over. So the reciprocal of 2/3 would be 1 over 2/3. 1 over 2/3 equals 1 divided by 2/3. And remember our rules for dividing fractions. 1 times 3/2. Anything times 1 is itself 3/2. So the reciprocal of 2/3, 1 over 2/3, is 3/2. We're going to keep these in mind before we get to their fancy names that you don't really need to know. You can call them opposite and reciprocal, but you are going to have to understand the property. We want to talk about the inverse property and the identity property. Let's talk about the word identity as it relates to math. Now, Identity is also a very good horror movie. No spoilers. I'll talk around it. Identity as it relates to math means itself. So just a little bit ago, what I erased here, I said anything times itself, or sorry, anything times 1 is itself. So for multiplication, what is that number that I can multiply anything by and get itself. With multiplication, that's 1. So the identity property of multiplication is that anything times 1 is itself. The multiplicative well, I should have known that was going to go off screen. Why would I write up there? The multiplicative identity is going to be 1. I'm going to keep that in a little cloud over here. Multiplicative identity is 1. Now, identity property of addition, just like we had commutative properties for multiplication and addition, we have identity properties for multiplication and division. We'll ask ourselves the same question, but instead of multiplication, addition. What is the number that we can add to anything and get itself? 0. Wouldn't be 1. Anything plus 1 is itself plus 1. But anything plus 0 is itself. This is the additive identity. A-D-D-I-T-I-V-E. Identity is 0. So the identity property of addition, anything plus 0 is itself. Now I know right now you might be thinking, oh my God, what is this guy doing? He's talking about everything. He seems to be starting things. And is he finished talking about any of them yet? What does this have to do with reciprocal and opposite? Why is he talking to himself like Jim Gaffigan? What does this have to do with a hot pocket? Okay, here we go. Here's where it's all going to come together. The inverse property. Let's do multiplication first. Let's find the number that we can multiply by anything that will equal the identity. And we're going to call it the inverse. This will be the multiplicative inverse, because we're going to use the multiplicative identity as our answer. We're going to try to get to 1. Well, guess what? We would have to multiply a times 1 over a to get 1, because a times 1 over a would be a over 1 times 1 over a, which would be a over a, and anything over itself is 1. 1 over, that's the reciprocal. So reciprocal and multiplicative inverse mean exactly the same thing. It's called the multiplicative inverse because it is the number that you can multiply by a number that brings you to the multiplicative identity. And what does that mean? It's the number that you can multiply anything by that doesn't change it, that gives you itself. So now that this is coming together, I'm going to ask a similar hypothetical question like I did earlier. Does this mean that this is all going to end with the additive inverse being the same as the opposite? Spoiler alert, it will. Let's do it. So the multiplicative inverse property is going to change to the additive inverse property. The additive inverse is going to be the thing that we add to a number to give us the additive identity. A plus what is 0? Well, A plus the opposite of A is 0. That's what an opposite is. Two things you add together that give you 0. An additive inverse is the thing you add to a number to give you 0. The additive inverse is the opposite. Now, again, I'm going to check in with you here. If all these big words are scaring you, if this is why you don't like math, then I want you to forget about all the big words. You don't need to know what the properties are in name. You need to know what the properties are in practice. And you do. Something plus its opposite gives us 0. Something times its reciprocal gives us 1. Anything plus 0 is itself. Anything times 1 is itself. Those 4 pretty basic math rules are what we mean when we say additive inverse property, additive identity property, multiplicative inverse property, multiplicative identity property. So if you know which one's which, great. But the important thing is that you can do plus 0 times 1, adding an opposite, multiplying by a reciprocal. Okay. So I purposely did the more complicated looking properties in the middle so we can finish off properties with one of the easier ones and then the most important one. So the easy one or set of ones that I skipped over, normally it would be grouped with the commutative. The associative. Interesting that I use that word. Usually it's grouped with the commutative property. Because another way of saying normally it's grouped with the commutative property is that normally it is associated with the commutative property. Associative property means grouping. For addition, if we had A plus B in parentheses plus C, it is the same as A plus and then in parentheses B plus C. So that's one way to think about it. But hopefully, as I've explained these properties, if I have made anything clear, It's that knowing the technical, this is the definition of the associative property, isn't what you need to take out of it. As long as you know how to use the property and what it is, that's enough. You don't need to be able to say, I used the associative property to do this. I said it's the grouping property. It's saying if we have a string, so A plus B plus C is going to be equal to A plus B plus C. They are exactly the same. There's no question that this is a true statement. The associative property says it does not matter what you do first. You could either add these two and then add the third, or you can pick these two and then add the one. So it doesn't matter which grouping of two you do first. That's the associative property. Associative property of addition has plus signs. The other associative property is the associative property of multiplication. It has multiplication signs. Now, when we're talking about variables, A times B times C can be expressed with dots. When you're first doing multiplication, you use the cross, the X cross for times. You can see in algebra, we don't want to do that because is that a times or is that an X? We use X a lot more than any other letter. So since multiplying is one of like 4, maybe 5 things we can do, it would be really confusing if one of the most common operator symbols was around, because that would be X times X. Is that X times X? Or is that 3 X's? We avoid that. In algebra, you don't want to use the cross. If you do, use star. The star is very clearly not a letter. The cross definitely could be a letter. That's the same reason why when we do algebra T's, T plus V looks weird like that. Are these pluses? Are they both pluses? So when you write your algebra T's, you want to make your T like that. T is not going to be a commonly used letter, but since it's a letter, it can be a variable. Any letter can be a variable. What was I saying? Oh, right. A times B times C. You can use the dots, and in fact, you need something. If we had numbers, 2 times 1 times 3, or we can put them in parentheses right next to each other, 2 times 1 times 3. With numbers, we couldn't just do nothing because that's the number 213. But here's the thing. If we did these same things with letters, okay, parentheses, that means multiplication. There's not a number ABC. There's not a letter ABC. We don't have the same issue that we do with 2 times 1 times 3 being a completely different looking thing than 213. And it's a lot easier to write nothing than it is to write something. And although the common mindset is that algebra is around to make things difficult, that's a lie. Algebra is around to make things easier, and the easiest thing we can do then is to write A, B, C when we mean A times B times C. It's the same reason why you see 3x everywhere and you don't see 3.x. There's no issue just jamming the 3 and the x together. If x were another number, if we wanted to plug, say, 2 in for x, we couldn't just replace the x with a 2. No, when we plug in for a variable, then we need to either use the parentheses or use the dot or use the star, but we would never just write it together when it's two numbers. So as long as it's not just two numbers, we can just jam things right next to each other and mean multiplication. So to explicitly say this, because every now and then there's something where I'm going to say, I don't want you to leave this class without knowing this answer. Honestly, hopefully you didn't come in to this class without already knowing. But if you didn't know then, you're going to know now. Let me move this out of the light spot. I'm so sorry about that. The answer to the question, what does 3x mean, has one and only one answer: 3 times x. So if you were stopped on the street and someone said, hey, what does 3x mean? You say 3 times x, have a great day. And then you keep walking because don't talk to strangers. Okay.